SwayamPrabha. Digital India. Educated India.
We have been discussing approximate methods for analyzing structural dynamic problems as a build up to the development of idea of finite element method. So, in today's lecture we will start talking about finite element method, what are the basic motivations, and start analyzing some simple problems. So, let us first quickly recall what we have been doing. So, with reference to a problem of beam vibration, this is the governing equation for a Euler-Bernoulli beam with specified initial conditions and appropriate geometric and natural boundary conditions. So, the general format of finding approximate solutions is to seek the unknown dependent variable in terms of a series like this, where phi n of x are known as trial functions which are to be chosen by the analyst, and a n of t are the unknown generalized coordinates to be determined through an analysis. So, the basic idea here is to we will substitute this assumed solution into the governing equation and we obtain an error or a residue term, and the whole idea of developing approximate methods is to drive some measure of that residue to 0 or as small as possible and use that criteria to select these generalized coordinates. So, this class of methods are known as method of weighted residuals. So, they lead to a discretized set of equations. Here A is a n cross 1 vector, M, C, K are all n cross n matrices, P of t is a generalized force which is n cross 1. We also discussed how to obtain initial conditions A of 0 and A dot of 0 in terms of specified initial displacement profile and velocity profile. Now, basically what does method of weighted residuals achieve? A partial differential equation governing the system behavior is now replaced by a set of ordinary differential equations with a view to obtain an approximate solution, and that approximate solution is encapsulated in this representation. So, we discussed several criteria for minimization of the residue, some measure of residue. So, we discussed method of least squares, collocation method, Galerkin method, subdomain collocation method, Petrov-Galerkin method, etc. In all these methods, the format of implementing the method of weighted residuals share certain common features. If we look at the way we obtain equations for A n, in least squares approximation we minimize the total mean square error and we get a residue term multiplied by another function. So, here also in collocation also we get the residue term multiplied by a weight function. So, this is common to all these methods. So, the format is therefore, we have the residue term and we select n weight functions and write these equation for n equal to 1 to capital N, thereby leading to a set of ordinary differential equations for the unknown generalized coordinates. Now, the implementation of this method therefore requires choice to be made on two quantities, namely trial functions and the weight functions. So, if you look at the residue which will be equal to this term minus f of x comma t, it has fourth derivative terms present in this example. So, consequently, the trial functions in this example need to be such that they are differentiable up to fourth order, but whereas the weight function does not, we need not impose any such requirements on the weight function. Now, this format is known as weighted residual format or the weighted residual statement for the given problem. The original partial differential equation is called the strong format of the equation. In the so called weak formulation, what we do is we want to now weaken the sense of continuity demand on the trial function and pass on some of that to the weight function. So, that is achieved by integrating this equation in parts by parts, thereby what happens is the continuity requirements on trial functions come down, and whereas on the weight function it goes up, and the requirements will be shared equally between the weight functions and trial functions, which the user anyway has to choose. So, that approach is known as the so called weak formulation of the governing equations. We also discussed another method known as assumed mode method, which is suitable for structural dynamic applications. You can assume the solution as in this form and directly work with the governing Lagrange equation to obtain the governing equations for A of t. So, we have discussed all this these methods, and what are the limitations of these methods. Now, in all these methods we are representing solution in this form, and this phi n of x are global in nature, that is they are valid for all x belonging to 0 to L. So, for simple line geometries, as we have been discussing in the example so far, the choice of this trial functions is reasonably straightforward. We can make those choices with reasonable effort. But however, if you are dealing with more complicated geometries or structures built up of line elements and so on and so forth, developing global shape functions is not a easy exercise. Another problem with this representation is these generalized coordinates a n of t, n equal to 1 to n, do not have a direct physical meaning, and we would like to deal with generalized coordinates if we could, where these coordinates have some direct physical meaning. Now, so to elaborate on what I said, if you consider a truss, a 3-dimensional truss structure like this or a frame like this, it is very clear that developing an exact solution for dynamics of this type of structure using by writing the governing partial differential equations for every member and establishing what happens at joints etc., you are unlikely to succeed. Even for this simple example, it will not be a straightforward exercise. So, exact solutions are difficult if not impossible. Now, approximate solutions using global trial functions are again difficult because it is very difficult to set up trial functions for this type of system. Similarly, for this type of, even for this simpler system, it is very difficult to set up the globally valid trial functions. As I again said, the generalized coordinates even in such these representations do not have direct physical meaning. Now, the finite element method basically aims to overcome these limitations. So, again let us now start by making some observations and some general remarks. What are the motivations for developing finite element method, and what are the generic features before we get into specific details. So, let me again summarize. So, the class of problems which can be solved exactly is limited. Of course, the exact solution have their own value. When they are possible, they serve as benchmarks against which approximate solutions can be validated. Therefore, study of exact solutions has a place in our studies. On the other hand, approximate solutions which imply global shape functions are possible for a limited class of problems. Again, we would like to work with methods in which the generalized coordinates have direct physical meaning. Unknown coefficients in a series expansion in terms of global trial functions do not serve this purpose. For most practical problems of engineering interest, neither exact solutions are possible nor can we construct global shape function based on these approximations. So, these are some of the difficulties. Moreover, we would like to deal with certain complexities in our studies which could include one or more of these. For example, we would like to handle geometric complexities, curved shapes, cutouts, large size structures, for example, nuclear power plants, cooling towers, bridges, long span bridges and so on and so forth, with foundations and piers and superstructure, all of them treated together. So, geometric complexity is a basic difficulty that we wish to handle. Similarly, inhomogeneity and structural material and geometric properties, say members need not be prismatic, thickness could vary, material properties could vary and so on and so forth. Then we may even deal with structures assembled out of simple structural elements like bars, beams, plates, shells and 3D continua. For example, a bridge structure will have soil, piers, superstructure and so on and so forth. So, different parts of the structure could be modeled using different structural elements. So, but we want to treat the entire assembly as a single structure. Then we want to deal with diversity of structural behavior, for example, static stress analysis, vibration analysis, buckling, fracture, fatigue, creep, parametric instabilities, bifurcations and so on and so forth. So, when we deal with practical problems, we should have handle on dealing with some of these issues. Another important issue is we would like to be able to deal with geometric or material nonlinearities and time varying systems. We will come to that examples of all this in due course. There are many problems where more than one physical process is involved. For example, in fluid structure interactions like pipes conveying fluids or liquid storage tanks subjected to earthquakes, so on and so forth, we would like to model the interaction between structure and the fluid. In thermal stress analysis, which is needed for example, in analysis of structures under fire, we need to combine heat transfer analysis with stress analysis. And in electromechanical systems like smart systems and things like that, the field variables could include certain electrical variables in addition to mechanical variables. Similarly, structures under active control, for example, buildings where we have active control mechanisms in place against earthquake loads. So, how do we deal with this variety of problems? We need a general framework where we can formulate these problems, analyze and try to interpret the results. Now, the finite element method is basically a powerful means to tackle some of these issues. The main idea of finite element method is that the field variable defined over a given domain is approximated in terms of piecewise polynomials over subdomains, and we assemble the solutions that we develop on subdomains suitably to get the solution for the entire domain. So, the use of piecewise polynomials lie at the heart of finite element method. Now, the finite element method has developed significantly in recent years. The main drivers for this is advances in computer hardware and software, and we have now professional softwares for using finite element method as a tool, which has three important components. It is not only that we use computers to solve the governing equations, but we also use the computers to even to formulate the problem, set up the mathematical model for a given structure by taking into account geometric details, constitutive laws and so on and so forth, and then arrive at the governing equations that need to be solved. The equations that need to be solved could be a set of algebraic equations or a set of coupled ordinary differential equations. It is not that we use computers only to solve those equations. Similarly, after we solve these equations, we use again the computers to process the results. So, it is not that we obtain solutions at all points on the structure in our analysis, but we need to know what could be the response at different points of the structure and how to display the results so that engineering decisions can be made. So, computers are being used extensively to deal with all these wide variety of problems, and this contributes to the wide success of the method. On the other hand, the mathematical foundations of the subject is also being well understood, and now study of finite element analysis forms a major theme in mathematics research. So, let me ask this question: finite element method, we have abbreviation FEM. What does this, what do these three alphabets mean? What is F in finite element method, that is what is finite in finite element method, what is element in a finite element method, and what is this method in the first place. So, we will address this problem of what is M. Finite element method is an approximate numerical method for analyzing mathematical models of physical phenomena encapsulated through a set of partial differential equations or variational principles. So, it is an approximate numerical method basically to treat partial differential equations or problems that can be formulated using certain variational principles. Now, we also have the phrase finite element analysis. Now, this can be taken to mean study of mathematical aspects of the method, including questions on how the various approximations may affect the convergence and accuracy of the solutions. So, this word analysis implies these addressing these questions. whereas method implies using the tools to solve engineering problems with a proper understanding of how the method has been developed in the first place. Now, to explain what is finite in finite element method, we will start with some observations. We generally work in Cartesian coordinate system. When we apply finite element method, we typically deal with vectors and tensors like displacements and stresses and strains and so etc. Therefore, we need a coordinate system. So, we use Cartesian coordinate system. Now, a field variable u of x tilde comma t, let us say that is a s cross 1 vector of dependent field variables which we need to determine, and omega is the domain of interest. So, x tilde is x1, x2, x3 which is a Cartesian space. Now, what finite element method does is it treats, we do not take the field variable u x tilde comma t as the unknown. What we do is we select a certain points xi tilde and the value of the field variables at these points, if there are n number of them, these are treated as unknowns, and we aim to determine this, and after knowing this we will develop an approximation to the field variables in terms of these n variables. So, the method employs, and also to develop these solutions, for this purpose the method employs piecewise polynomials to achieve that. That is again a very important aspect of the method. So, therefore, the problem of approximating the infinite number of unknowns, that is u of x tilde comma t for all x tilde belonging to omega and for all t greater than or equal to 0, is now converted into the problem of determining a finite set of functions u of xi tilde comma t I running from 1 to n. So, this is what makes the name finite in finite element method. This is what this aspect of the solution contributes to this nomenclature. Now, the points in the domain where we the field variables are taken as unknowns are known as nodes. Now, we also call this as the value of the field variable at these points are degrees of freedom at the node I. These are the generalized coordinates which typically have a direct physical meaning, because they are the values of the field variable at the nodes, they have an immediate physical meaning because the field variable itself has a physical meaning for in a given problem. Now, in this discussion the time variable t is still continuous at this stage. I have not talked about discretizing time. So, we call this discretization as semi discretization, only spatial variables are discretized, the time is still treated as a continuous variable. So, now the question is how this u of x tilde comma t is approximated in terms of these degrees of freedom. This leads to the notion of element, that the E in the finite element method. What does that mean? So, you consider a domain omega, suppose I partition this omega into a set of I equal to 1 to r as shown here, this is one ith element. We say that these omega i's whose union contributes to the domain, and we expect that there is no intersection between these sets. That means omega I intersection omega j is a null set for all I not equal to j, and omega I is known as the ith element. So, this element itself now need to be characterized in terms of geometry and how many nodes it has. I have shown for each element here, for this type of element 3 nodes, but whereas if you look at this there are 3 nodes. Then how many field variables are treated as unknowns at a given node, that depends on problems as we will shortly see, and what is the total number of unknown coordinates that is assigned to each element, that is known as total degrees of freedom for the element. Then value of the field variables within the element, how do we determine? Suppose I know value of the field variable at the nodes, how do I get the field value of the field variable within an element? So, these are some of the issues that we need to address when we talk about an element. So, what we do is, suppose if you consider this element, I name these 4 points as nodes 1, 2, 3, 4, and what we do is within an element we approximate the field variable by interpolating the value of the field variables at these 4 points. So, we write this as j equal to 1 to q, q is 4 in this illustration, and this is the value of the field variable at 1, 2, 3, 4 and these are known as the interpolation functions. So, nj of x tilde are interpolation functions. What we do is we choose these interpolation functions to be polynomials. The nature of this choice is paramount in determining the quality of the solutions we get. So, this is a very vital aspect of implementing the method. So, what are the typical steps in finite element analysis of say a structural dynamic problem? So, what we do, we partition the domain into a set of elements. Now, this domain omega actually we may not be able to represent exactly in a finite element model. For example, it has curved edges. So, in our modeling even the domain is replaced by an approximation. So, those details we will come to as and when we encounter curved boundaries and things like that. So, even these curved edges need to be suitably approximated. It is not that the given domain omega with all its complexities is exactly replicated in our model. So, that also should be emphasized. So, that we partition the domain into a set of elements, then we approximate the behavior of the field variable within each element either starting from the governing partial differential equation or the relevant variational principle if it is available for the given problem. We use trial functions, as I said trial functions are piecewise polynomials. This leads to element level structural matrices. Typically in dynamics we get element mass, stiffness and damping matrices and vector of nodal forces. Next, we have now partitioned the domain and analyze each bit like this. Now, the next job is we should put back all this and form the built up structure. So, we assemble element level matrices and force vectors to form the global matrices and force vector for the structure. This is assembling. Then we look at the boundary conditions to be imposed, right. After we impose the boundary conditions, we obtain the governing set of equilibrium equations for the problem. Typically in these applications there will be a set of ordinary coupled second order coupled ordinary differential equations. They could be non-linear if the underlying problem is non-linear, otherwise it could be linear. Now, for these set of ordinary differential equations, we now address the question of discretizing the time. So, we typically use time stepping methods, explicit or implicit depending on the details of the problem, and this completes the determination of the field variables at the nodes. Then we compute derived quantities like stresses and strains. If displacements are the degrees of freedom, which in most of the applications is the case, then we need to derive strains, stresses at the nodal values at the nodal node points as well as in the interior. Okay. So, that completes the solution. We need to consider several other points. I will just make a brief mention of these points and we will return to some of these issues as we go along in the course. So, we have said that we have defined element through this description. So, the given domain is partitioned into a set of R subdomains which are mutually exclusive and collectively exhaustive, and we call omega I as ith element. This also defines the division of geometry. Now, the word mesh is used to denote the collection of elements which replaces a domain omega in the simulation work. Now, we need to address question on inter-element behavior of field variables. So, we should note that the communication between two distinct elements is only through the value of the field variables at the nodes, it is only through the points, common shared points. We do not talk about interaction through lines or surfaces, it is only through points even in 2 dimensional and 3 dimensional problems. Because in 2 dimensional, in a line element the two elements are connected through a point, but in a plane element 2 dimensional element the two neighboring elements can be connected through lines, and in solid element 3 dimensional elements the neighboring elements are connected through surfaces, but the interaction is always through nodes, that are the points. Then how do you evaluate the derived quantities, for example strains and stresses within an element, and how do these quantities behave across the element boundaries. So, this is an interesting question. We will see that there are some difficulties in modeling this, and this is one of the concerns that we should be aware of. Then we should look at quality of the answers obtained. So, there are many decisions that we have made, how many elements that we should take, how many elements, that means how fine should this partition be, right, that we call it as H. H indicates in some sense the size of the element, and within an element what order of polynomial we should use to interpolate the field variables, that determines P, and delta t is the time step that we need to use in integrating the semi discretized equations. So, the accuracy of the solution finally depends on a combination of H, P and delta t, right. So, we need to understand how to make these choices to ensure that we get acceptable results. So, now to develop this discussion on finite element method, the approach that we will take is we will start by developing structural matrices for different types of elements, like axially vibrating bar, a torque element, 2 dimensional and 3 dimensional beams, then plane stress and plane strain elements, plate bending element, shell element, 3D solid element and so on and so forth. So, for each of these we will develop we will characterize the behavior of a single element, and then we will address question of how to assemble the formulations at element level and study structures such as trusses, planar frames, grids and 3D frames, and also certain 2 dimensional and 3 dimensional continuum structures. So, this is the broad outline of at least the next few lectures. So, we will start somewhere, we will start with addressing questions listed here. As a prelude to that, we will quickly review some notations and equations from linear elasticity for isotropic material. So, the independent variables and the coordinates of the system, we use x, y, z or x1, x2, x3 and time t. So, there are 4 independent variables in a 3 dimensional problem of elasticity. One is time and 3 are spatial coordinates. Now, we can make a coordinate transformation. So, we can have one coordinate x1, x2, x3 a coordinate system, another one x1 prime, x2 prime, x3 prime, and we would like to know how to transform quantities described in x1, x2, x3 to the new coordinate x1 prime, x2 prime and x3 prime. The coordinate transformation matrix for a position vector is given by this well known transformation matrix. This is an orthogonal matrix, we will be using some of this quite often. What are the dependent variables in elasticity problem? The state of stress at a point is given by the stress matrix which is 3 by 3 symmetric matrix, and each component will be a function of x1, x2, x3 and time t. Then we also have strain components, which is again a tensorial quantity, and it is described by another 3 by 3 matrix which is again symmetric and which is again function of the 4 independent variables. Displacement component, there are 3 displacement components u1, u2, u3, and they are again functions of the spatial and time coordinates. So, the total number of dependent variables is 15, independent variables are 4. Now, how do these dependent variables behave under coordinate transformation? Sigma stress and strain are tensorial quantities. So, they undergo transformation through these rules, where T is the transformation matrix between the coordinate system. So, sigma prime is the state of stress at a point in the transformed coordinate new coordinate system, and this is the sigma is the state of stress with respect to a reference coordinate system. Similarly, strain, and this is displacement is a vector, this is how it translates. Scalar quantities are invariant with respect to coordinate transformation. So, now we have 15 unknowns and we need to now generate the 15 equations to tackle this problem. As we know, there are 3 equilibrium equations, 6 strain displacement relations and 6 stress strain relations. So, I have listed these equations here for quick reference. The equilibrium equations have terms involving gradients of stresses, and also these capital X1, X2, X3 are the body forces. There are forces which are proportional to the volume, and rho is the density, u1 double dot, u2 double dot, these terms on the right hand side represent the inertial forces. Okay. So, sigma ij is same as sigma ji, therefore, there will be 3 equilibrium equations. The strain displacement relations are given through this set of formulae. Again strain epsilon ij is epsilon ji, these are normal strains, these are shear strains, the 3 normal strains and 3 shear strains. Now, for a Hookean material, the stress and strain are linearly related. We can show that there will be 2 independent constants. In terms of Lamè's constants, the constitutive laws can be given like this. The way the stresses are related to the strains is through this. The E is the sum of the normal strains, and in terms of that we have this constitutive law. These are the stress strain relations. In terms of you can also express strains in terms of stresses. This is the first invariant of the stress matrix, and we get these relations. Again, this is in terms of Young's modulus and shear modulus. So, we could use either this or this depending on the context in which we formulate the problem. If you use indicial notations, all these equations can be written in a compact manner. So, this is the equilibrium equation, set of equilibrium equations, this is the set of strain displacement relations, and this is the stress strain relation. I, J, K, L etcetera take values from 1, 2 and 3. So, the repeated indices imply summations, a comma is a differential, all those notations are used here. Now, there is yet another way of representing stresses and strains. Here we write the state of stress at a point as a 6 cross 1 vector, instead of a 3 by 3 matrix, a symmetric matrix, we write it as 6 cross 1 vector, and the strain is written in this form. So, this is not a tensorial quantity anymore. So, this is the strain, and if we now write the stress strain relations in this notation, this C will be a 6 by 6 matrix, because stress is a 6 cross 1 vector and epsilon is 6 cross 1 vector. So, either we can write stress in terms of strain or strain in terms of stress, and these matrices obey this identity, and we have these expressions for the C matrix and C tilde matrix, and nu is the Poisson's ratio, E is the Young's modulus. So, this is for an isotropic material. Now, if we define an operator D as shown here, this is 6 cross 3 matrix operator, we can write the governing equilibrium equations, and in this form D transpose sigma plus x is rho u double dot. Now, the strain displacement relation using the same matrix can be written as du equal to epsilon. Now, here if I now use the constitutive law, sigma is equal to C epsilon or epsilon is C tilde sigma, and if suppose if I substitute here. So, I will write for sigma C e, then this equation becomes D transpose C epsilon plus x equal to rho u double dot. Now for epsilon I will write now du. So, if I write that, I get this as the equations, governing equations, where the equilibrium equations, stress strain relations and constitutive laws are all being captured, and this the final equations are written in terms of displacement components. Okay. So, D is this operator, C is the constitutive matrix of constitutive laws, and this is the body force, vector of body forces. Now, we will also need a general approach to derive the strain energy in a body under a multi-axial state of stress. So, we will start by discussing how to derive strain in a uniaxial state of stress. Suppose at a point in the structure we choose an infinitesimal element dx dy dz or volume dx dy dz, and if sigma xx is the only non-zero stress component, the forces on this face is given by sigma xx dy dz. Now, the work done by these forces on the deformation can be computed over this entire volume. The force is sigma xx dy dz and the displacement is strain into dx, this is this, and half because the load is applied, the deformation take gradually, and we can write this as sigma xx epsilon xx dv, integral over v multiplied by half. Now, if the body is in a multiple state of stress, that means all stress components are acting simultaneously, then this logic can be extended, and the equation for strain energy over the entire volume can be written in terms of the stress vector and strain vector in this form. Okay. So, now if we substitute the constitutive law and use the strain displacement relation, the strain energy can be expressed in terms of the displacement components, the operator D and the constitutive matrix of constitutive coefficients in constitutive law. So, this is the expression for strain energy in a 3D solid under multi state of stress. So, this is strain energy, this is the kinetic energy, right. So, the Lagrangian is this and we can define the action integral. So, if we now apply the select u so that action integral is minimized, we recover the equations of elasticity. Okay. So, this is a general framework for treating 3-dimensional elasticity problems. Now, as a special case we will start now talking about simple elements. We will start with discussion on axially vibrating rod element. So, I consider a rod element of length L, axial rigidity AE, damping C and M is mass per unit length. So, this is a cross section and the coordinate system x is along the length of the bar, y is as shown and z is shown here. Now, this rod will be in a state of uniaxial state of stress. Therefore, the state of stress is given by sigma xx x comma t, that means all other stress components are 0. So, this is a standard assumption that we make in modeling axially vibrating rods. So, strain is consequently given by this and the displacement is only function of x and t. Now, if I use that now in the expression for strain energy, we will get now the strain energy expression as this, kinetic energy is this and the action integral is this. Now, we want to now develop the finite element approximation to handle this element. So, what we do is we define these two ends as nodes. So, that I have shown as these numbers in a circle 1 and 2 are nodes. U1 of t and U2 of t are the values of the field variable u of x comma t at node 1 and node 2 respectively. P1 of t and P2 of t are the stress resultants at 1 and 2. Now, we will consider the equilibrium of the bar under the action of support displacements u1 and u2. So, suppose phi 1 is the trial function that we are going to work with, we need phi 1 of 0. That means, what we are doing is we are going to approximate the field variable in terms of the value of the field variable at the nodes. That means, we are interpolating. Suppose I want a state of stress here, the field variable here, I will interpolate the values at these two nodes and this is a representation, and phi 1 of x and phi 2 of x are the trial functions. Now, how to select these trial functions, that is a question we are asking, and what we do is we will assume phi 1 of 0 is 1 and phi 1 of L is 0. This is the equation under these displacements and we get phi 1 of x is 1 minus x by L. Similarly, we get for the other displacements phi 2 of 0 is 0, phi 2 of L is 1, we get phi 2 of x as x by L. That means, we are basically using linear interpolation functions. So, what we are doing is we are taking u of x comma t as u1 of t into phi 1 of x plus u2 of t into phi 2 of x. The u1 of t and u2 of t are the generalized coordinates. We call phi 1 of x and phi 2 of x as trial functions. So, now u of 0 comma t is u1 of t, because at x equal to 0 the prescribed displacement is u1 of t. So, if we use that, u of 0 t, comma t is u1 of t phi 1 of 0 plus u2 of t phi 2 of 0. So, consequently, I get phi 1 of 0 is 1, phi 2 of 0 is 0. Next, u of L comma t is u2 of t. So, if I impose that condition, I will get phi 1 of L is 0, phi 2 of L is 0. Now this ensures that if we select now phi 1 and phi 2 so that these 4 conditions are satisfied, this ensures that we have satisfied the requirements on displacements at x equal to 0 and x equal to L. Now the previous slide I discussed on how to select this phi 1 and phi 2 under the required conditions, that is this one and this one. So now we are ready with the interpolation functions, which are 1 minus x by L and x by L, and the approximation for the field variable as shown here. Now I can find the velocity field by differentiating this with respect to the time. I will get u1 dot of t into this, u2 dot of t into phi 2 of x. Similarly, I can get the derivative with respect to x, this will be this. Now I can substitute this into my expression for strain energy and kinetic energy. The strain energy is given by half A e dou u by dou x whole square. So if I now substitute that dou u by dou x, as you have seen here, it is u2 minus u1 by L, it is independent of x. So I can quickly evaluate this. Next, kinetic energy, this is half m u dot square. So u dot is u1 of t 1 minus x by L, u2 of t x by L whole square dx. Now these are polynomials, simple polynomials, so I can quickly integrate this. So if I do this, I get this as the kinetic energy in terms of the two generalized coordinates, and this is the strain energy in terms of the generalized coordinates. So now I can form the Lagrangian. The Lagrangian is t minus v, I get this. There are 2 degrees of freedom and I need to run the Lagrange equation for u1 and u2. So that involves finding gradient with respect to u1 dot and u2 dot, and substituting these terms we can easily derive all this, and we get the equation governing u1 to be this, the equation governing u2 to be this, and now I can recast this in a matrix form. I can write an acceleration vector u1 double dot plus u1 double dot and u2 double dot, and this gets multiplied by the so called mass matrix, and u1 and u2, which is a displacement vector, which gets multiplied by the stiffness matrix. So I will come to this force vector in due course, but we can believe that these are the nodal forces. So I get now the equation, element level equation of motion of the form mu double dot plus ku equal to p. Now we can make few observations. This m, which is ml divided by 6 into this, is known as element mass matrix. We also call this as the consistent mass matrix. Why? What is the genesis of the phrase consistent here? It is consistent mass matrix because the shape function that we have used for computing the kinetic energy is same as the one used in computing strain energy. So that means in that sense it is consistent. It also implies that there is an alternative way of finding mass matrix which is not consistent. I will come to that shortly, and you can see that mass matrix is symmetric, and this quantity k A e by L into this matrix is known as element stiffness matrix. It is symmetric, and we call this element that we have developed as a 2 noded bar element with 1 degree of freedom per node and 2 degree of freedom for the element. This k and m, we should also notice that they are non-diagonal, they are not diagonal matrices. So the nodal degrees of freedom are coupled in this representation. Now I talked about consistent mass matrix, and an alternative way of deriving mass matrix used to use heuristic arguments, and in an element half the mass is lumped at one end and half the mass is lumped at the other end. If we do that, we get mass matrix to be diagonal, and this is called lumped mass matrix. This is diagonal, but it excludes inertial coupling between the nodal displacements. The earlier formulation showed that these quantities are not 0. So obviously that coupling has not been considered in this formulation. Lumping is to some extent an arbitrary process. In this case it may seem intuitively acceptable, but when it comes to elements where there will be flexure, as we will soon see, lumping this mass matrix may not be straightforward. Now we can make some more observations. We have now this representation u of x comma t is 1 minus x by L u1 of t plus x by L u2 of t. Suppose both the nodes are given equal displacement of unity, that is the rod is undergoing a rigid body displacement. In that case what should be u of x comma t? It should be 1, because there should be no elastic deformation of the bar, and that is consistent, we do get that. So, this means phi 1 of x plus phi 2 of x is 1, and we call this property as partition of unity. Now, let us again take a look at the assumed representation for the field variable. Now, let us, this is displacement, let me compute the strain. We get strain to be independent of x. Okay. So, strain is independent of x for any L. So, that means constant strain condition can be simulated as element length goes to 0. So, in a finite element model, as element becomes smaller, we expect that there will not be any strain variation within an element, and that is simulated correctly here. So, these two properties are of they have serious implications on convergence of finite element solutions, and at some later stage we will revisit these issues again, but at this stage we can make these observations. Now, we are ready to tackle some quick examples. So, suppose there is a rod which is clamped at this end and it carries an axial load like this. So, suppose I model this using one element, we see that this bar is clamped here, therefore, u1 of t is 0, and at this end I am applying an external force p of t, therefore, p2 of t should be p of t. Now, if I put that into my governing equation for the element, I get for u1 double dot is 0, u1 is 0, and at p1, that means at this end there will be an unknown reaction. Okay. So, that is r of t, which is not known. On the other hand, there is an applied force that remains as p of t, and u2 is the field variable, u2 of t is not known. So, there are essentially two equations for two unknowns. One equation is for the unknown nodal displacement u2 of t, other equation is for the unknown reaction at node 1. So, now if you write the second of these equations, I get the governing equation for the unknown nodal displacement, and sorry, this is the equation for reaction, the first equation, I get reaction in terms of u2. Now, the equation for u2 itself can be obtained by considering the second row here, and we get this equation. So, if you carefully look at the structure of these equations, it follows that first you need to find u2 of t using this equation and then substitute back into this to get the reaction. So, if you look at this equation now, I get this is a single degree of freedom approximation, there is only one generalized coordinate. So, I get this, an approximation to the natural frequency according to this model is this, and u of x comma t is x by L u2 of t, u2 of t is solution to this, and the strain is given by this, the stress is given by this, the axial thrust is given by this. So, we have found out now the displacement, strain, stress, stress resultant and the reaction. So, this framework enables you to do that. Now, let us consider the situation to understand the nature of approximation that we are making. It is useful to consider a bar as shown here, and suppose I make 5 divisions here. See, the statement I made was in finite element method we use piecewise polynomials to approximate the behavior of the field variable for the entire structure. So, let us make now 4 subdomains as shown here, and within an the u of x comma t is the unknown displacement field all over this for x varying from 0 to L, and this is written like this. So, when viewed like this, what are the shape functions, what are the trial functions? The first trial function in our model will be this. This has non-zero value only over for the first element, and it is 0 here. It is linearly varying within the element. The second element, the second function psi 2 of x is in terms of these 3 nodal coordinates, and this is linearly varying as shown here. So, similarly the other elements are shown here. So, what we have done just now is we have considered the behavior of only one element and got the equation of motion for this element, but we need to actually study a built up structure like this. So, we need to find equations for A1, A2, A3, A5. Now, we will come to that in due course, but I want you to make a note of some simple things. See, what we are doing is at the element level we are using these as the trial functions, but at the built up structure level these are the trial functions, but they are all related. Now, how do we see that? Suppose I take the element E, the way I am interpolating UE of t is through these 5 functions. It is in terms of the element nodal coordinates and the element level trial functions. So, this is the kinetic energy for the element and this is the potential energy for the element. So, the superscript E here refers to the element E. Now, that means for each element I can do this exercise of computing the strain energy and kinetic energy using the local interpolation functions, and when it comes to computing the total strain energy and the kinetic energy, I can add contribution to this from each of these elements as shown here. Okay. So, this is what we will be doing when it comes to question of assembling the matrices. Now, we can extend this logic now to problem of Euler-Bernoulli beam. So, I will begin discussing this and we will continue with this in the next class. So, the problem description is as shown here. This is one beam element, it is characterized in terms of flexural rigidity EI, mass per unit length m, length L, and C is the damping properties, and this is the x direction in which the displacement field is u of x comma t, and this is the y direction where displacement field is v. Now, we are therefore considering bending in xy plane. We are making an assumption that the x axis coincides with the centroidal axis of the beam, and we also assume that there is no coupling between bending and torsion. This is not, this cross section is symmetric, therefore, there is no coupling between bending and torsion. So, if we now follow the tenets of Euler-Bernoulli beam hypothesis, u of x y comma t is given by this, because plane sections which are normal to the neutral axis before bending remain plane and normal to the neutral axis after bending. So, if you make those assumptions, if you use those if you use that assumption, we can write displacement like this. Now, v is a function of x comma t. Now, from this I can get strains. This is the normal strain, this is the shear strain turns out to be 0 in this model. So, I can compute the strain energy, we need to use sigma xx and epsilon xx, and if you use, this is an integral over volume. So, now I will integrate over x and area of cross section separately. So, using the assumptions that we have made, we get for epsilon xx whole square minus y dou square v by dou x square whole square, and that remains here, and the remaining integral, that is integral A y square dA, is nothing but the moment of inertia about the z axis. So, I write this equation. So, this is the strain energy stored in the beam due to bending. The kinetic energy is integral over volume rho v dot square dV, and again the dV, if I write it as dx into dA, I can write m as integral A rho dA, this will be the mass per unit length. So, I will get the familiar equation for the kinetic energy. So, the Lagrangian for the system is T minus V, and this is the expression for the Lagrangian. So, in the next class what we will do is, we will consider the beam element to have 2 nodes, and at each node we will consider field variables to be the translation and rotation. This double arrow notation is for rotations. So, this is rotation using right hand rule convention. So, u2 and u4 are rotations, u1 and u3 are translations. So, collectively we call them as displacements. So, associated with them there are stress resultants. So, we assume the field variable which is v of x comma t, which is the transverse displacement of the beam, in terms of the nodal, translations and rotations, and we need to therefore construct a solution, we need to construct 4 interpolation functions to achieve this. So, we will see how this we can do in the next lecture.